Hello, this is Randy, WB0SMX. There's a new group project starting on the QRP Tech Yahoo group to build a simple signal generator. Name of the generator is the 8640 Junior, so named because it's inspired by the venerable Hewlett-Packard 8640B commercial generator that so many of us experimenters have. This project was conceived as a learning project with an overall leader, Chuck Adams, K7QO, and others getting involved along the way to chip in. One of our first homework assignments was to use the LTSpice circuit simulator to build up and simulate various parts of the overall circuit. The first suggestion was to build up the buffer stage that precedes the divider string. This video is to walk through that process using LTSpice. So within the overall LTSpice window, you've got all your tools up here, and the first thing we want to do is start a new circuit by clicking on that little white LT up there. So that starts a new circuit, and then we can simply start placing components. This is a fairly simple common emitter amplifier. So of course it has to have a bipolar transistor in it. So the first thing we're going to do is look for a bipolar transistor in the components tool up here. So we click on that and we look for like a binary junction transistor or something along those lines. Let's try bi here. Nope, that's not it. Bi to oh, here we go. Actually, in these tools, it's an NPN or an NPN2. I don't know which one yet. Looks like an NPN is the right guy. So we'll say OK there, and we'll just place that transistor right in here somewhere. Now, once we've placed it, we can hit Escape, and then that makes it so you're not placing multiple ones as you click around in the box here. So if we use our scroll wheel, we can actually make that smaller and increase the area that we have to build in. So we've got a transistor there, and now we need some resistors. So with that, we come up here to the resistor symbol, and we can click once on that, and without holding down any buttons or anything, we just drag it around until we get it approximately where we want it. I'm going to say right there, and all I did with there was just click once and release. So each time you want to place one, just click once and release. So click release. So that's the second resistor. Now to rotate a resistor, you can use Control R, and that rotates really any component. So we can place that out here, and then we need a collector resistor. So I'll do another Control R, and that'll put it in the vertical plane again. So click there, and that ought to be about all the resistors that we need, so I'll hit Escape. So then we need one capacitor, so we can click on a capacitor here, and again, without holding anything down, we just move the mouse to the place where we want the capacitor, which will be somewhere right in here, and I'll use the Control R to flip it around and click and release, and that puts it there. Now if I was to click somewhere else, it would place another one. I don't want to do that, so I'll just hit Escape. Okay, so that's pretty much all of our components. I guess I could put one more capacitor in there for the filter for the power supply. I'll go ahead and do that, and that'll come let's say over here somewhere, and then Escape. Okay, so let's just start hooking things up here. We can use a wire. Now with all these tools, basically you're just clicking and releasing to select it. In this case we get a set of crosshairs, and each time we want to start a wire we click and release, and when we want to stop the wire we click and release a second time. So I'm going to start here, click release, click release, click release, click release, click release, click release, and you guys see how it works. Click release, click release. Okay, let's go from the collector to the resistor, and from the resistor. Now this time I clicked and released where there was nothing, and that allows me to slide over to the next component. Now if I move my cursor around, you see that it always goes in 90-degree angles here. So, and that makes it very easy. But there are ways to get around that, but I like the 90 degrees, so we'll keep it like that. So I'll click on the capacitor there. And that's enough for now, so I'll escape. Now we always need ground. LTSpice requires a ground somewhere in the circuit. Everything is referenced to that ground point. So even if your circuit is battery powered or something like that, always put a ground somewhere on the circuit, and it'd probably be on like the negative side of the power supply. So I'll put a ground down here, and we can have multiple ground points, or we could tie them together with a wire that would go, right there. I'll use multiple ones because I think that's a little neater. There, and then I'll put one here by the capacitor as well. And yeah, that's enough for now. So then I'll go back to making wires, and I'll just hook a wire to the ground, and from the emitter to the ground, and from the resistor to the ground, and escape. Okay, so it's coming along pretty well. We still need a wire to go from the bias resistor here. Click release, click release, to get its voltage for the base bias. And that's getting us pretty close. We're going to need a power supply. The power supplies are under these components, and you just come over to voltage, and we'll just say OK, and let's put a voltage here. And we also need a signal input, and that uses the same component, it's just configured differently. So we'll put a signal source over here and escape. A couple more wires. There, there, and here, here, escape, and we need a couple more grounds. Now we could tie the grounds directly to the to any component. I like to use wires, and it just seems to separate them a little bit and make it a little neater. And I also try to line them up, with other components, but not always real good at that. Ground, escape. Okay, a couple more wires to connect the grounds to the appropriate spots. Escape. Okay, so that's basically our circuit. I'm going to move this capacitor a little bit because I don't like that writing being right up against the wire. It's just an aesthetic thing. We can move things with this move component hand, or we can drag it with the drag component. I like that better for this circumstance because it keeps it connected to the circuit no matter where I drag it. So I'll put it right there, and then I'll actually drag these wires up here and here. Escape. Okay, so there's our circuit. We have a voltage source, which will be filtered by a capacitor, a collector resistor, a bias network for the base, the emitters tied to ground, a signal level resistor, I guess I'd call that. It's going to drop how much we're driving the transistor at, and a signal source. So now we have to start assigning component values. So let's just start over here with the voltage source, and if we hover over a component, you can see you get the little hand with the finger pointing out there. And what we can do is, if we hover over the component and right click, then that brings up the box that we can specify what it is. In this case, this is a 5.0 volt generator, and we don't need to get any more fancy than that. This capacitor is a 0.22 microfarad. So I'll hover over it, right click, and we can put 0.22. You don't need the leading zero, but it's nice. And then a U for microfarad. If you forget the U, that'll be a 0.22 farad capacitor, and you usually don't want that. Okay, this resistor is a 1K, I believe. Yes, 1K. So 1K, and say OK. This resistor is a 10K, so 10K, and OK. This one is a 4.7K, 4.7K, OK. This capacitor is a 100 picofarad, 100 P for pico. And this resistor is a 510 ohm, so we can just do 510. And now the voltage source, we're going to want to send a sine wave into this basically and see what we end up with for an output. And so for a sine wave, what we want to do is right click, and if it's anything other than a DC voltage, you have to go to the Advanced tab. So we go to Advanced and we say, okay, that's a sine wave. We're going to give it 0 volt offset, and I don't know, let's try 2.5 volts. I haven't simulated this out, so I don't know what the driving level is at this point, but we'll start with that. Frequency, let's go mid-scale for this guy. Let's say 20 megahertz, and megahertz is kind of weird for this frequency. M, just a capital M, does not work. You have to do MEG. Kind of ugly, but that's just the way it is. And we can say OK there. Alright, so last thing we need to do is basically, I don't remember if we need to put something to start it there or not. Let's just see what it looks like. I'm going to save this. Save. Saved it as a draft, so let me save as. And I'll save it as 8640 Junior Q4. Save. So that way, if we do something really bad, I can come back and load it in without going through all this stuff again. So at that point, we can pull up our simulate, and the edit simulate command is what we want. Edit simulation command. So first off, we just want to do what they call a transient analysis, And what that does is just basically a waveform analysis. It shows the waveforms at the different points in the circuit. And I'm going to give it a 1 microsecond stop time. So it's going to start at 0 microseconds, and it's going to stop the trace at 1 microsecond into the running. And that's really all we need. So we can say OK, and that gives us a little box here that we can put basically anywhere on the circuit. I usually put it down here. So that's there. And finally we can do a run. Oh, there's nothing there. Well, that's because we haven't selected anything to look at yet. Let's look at our input, say on the base. Okay, looks like we might be overdriving it a little bit. It's kind of flat topping up on top here, and so we might want to reduce that drive level a little bit. But we can also look at our collector output then, and we can see that it's definitely overdriving it there. It's definitely a square wave. So at that point, what we can do we can I usually just close this, and then I'll right click on this guy, and instead of driving it at 2.5 volts, let me drive it at 0.5 volts. And then I'll run the simulation again and select our input. Still a little hot. Select the output. Still hot there too. Okay, well, let's look at dropping that some more. .1 volt, 100 millivolts. Okay. Run our simulate command. Look at the base again. That's looking a little better. And our output looks nice and clean now. So that's basically how you do that. Works out pretty well. The other thing we can do, if we close this, we can come up to our simulate edit simulation command again, and instead of doing a transient analysis, we can do an AC analysis. This is kind of cool. Let's select decade, and what that does is it'll start on the left at whatever our starting frequency is, and every time it's a multiple of 10 times that, it'll give us a little marker. So I'm going to say 20 steps per decade, and I want to start it at let's say 12 megahertz, and I want to stop it at 50 megahertz. Now this overall 8640 Junior signal generator is designed for the oscillator, the base oscillator, to run at 13.6 to 31 megahertz. So that encompasses that whole range. So we'll just see what it looks like. So I can say OK, and I'll place that there, and I'm going to turn that one into a comment so that it doesn't actually run. So it's only going to run the AC analysis. So what that will do when we hit run now, what have I done? No AC stimulus found. Oh yeah, okay. This part here means that we didn't set up our input correctly. We need to basically set up this signal source to sweep instead of just be a set frequency. So I can right click on that, and I'll select over here AC amplitude 0.1, and yeah, I think that'll work. Let's see what that does. We'll run it again. Got it that time. And let's look at our output first. Okay. Well, we can see that it has a little more gain actually as we go up in frequency. And this is the actual plot of the signal amplitude as we move along in frequency on the horizontal axis. We're starting at 12 megahertz and then going up to 50 on this side. And this tells you how much gain there is. There's not a lot of difference there. 2.64 to 2.82 doesn't amount to a whole lot. So not too concerned about that. The other thing that we forgot to do in the beginning, let me close this again, is we forgot to select a transistor. So I right click on the transistor and it brings up this box here, and I can say pick new transistor. And of course 2222 is the first, 3904 is the second. This circuit is designed for a 3904. So I'll say OK on that. And then I'll run the simulation again. And look at our output. Well, it's different now. Okay, so now it has actually loss. So this is a real transistor. You know, it's kind of not unusual to see gain fall off at a higher frequency. So in the frequency range that this is designed to be used, which is about here, it runs so maybe 5 dB down from the input to 15 dB there, but we only go up to 31 megahertz, so about 11 dB. So it has about a 5 dB loss as it goes up to the maximum frequency. Not too bad. I think that's okay. So that's how that works. We can go back, close that, and change this guy back to a transient analysis. Okay. And I'm just going to take my scissors and I'm going to delete that other one that was just a comment. So now we're back to our just plain tran down there. I'm going to go ahead and save that. And let's escape. Right click this and get rid of this part again. So now we're back to just a set frequency for the sine wave. Save that. Run the simulation. And look at our output. Still looks pretty good. So that's how it works. So good luck with building your own. Thanks.